The new soil module is a separate, general-purpose module which enables more accurate modeling of the soil structure interaction through the better approximation of the boundary conditions of the structure. The aim of the model is to analyze and investigate the effect of soil deformations on the structure and to analyze and investigate the stresses and deformations in the soil. Soil module offers two approaches. First one is a more straightforward approach building on top of already available functionalities, which is the 1D, 2D Winkler support stiffness calculation, but based on the soil profiles under the individual support elements. The second one is a more sophisticated approach where the structure and the soil forms a coupled model. The soil is modeled with 3D soil elements using the real subsoil profiles and properties. The foundation of both approaches is the so-called terrain model, which is a 3D information set containing the soil profiles and the location of these soil profiles inside the modeling area. This terrain model is built up from the so-called borehole samples. The borehole sample function is accessible through the Elements tab, and it is a separate object which contains information on the subsoil layers and its location in the global modeling area. After having the terrain model built up, there are two options to choose from. First, let's check how the 1D, 2D Winkler support stiffness calculation approach works. A combination of a soil profile, the parameters of the footing, and the calculation is called a Winkler spring, representing an estimated support. This existing functionality has been improved, so if there are a terrain model available, soil profiles can be interpolated under each nodal, line, or surface support points from the stratigraphic model. This way, Winkler springs can be calculated in mass without the need of going through each support and adding their corresponding soil profiles. Let's see what it looks like in the software, what we've been shown so far. The model which will be used is a simple multi-story building. The concrete columns are supported by nodal supports, and the demonstration will show how the Winkler springs can be calculated automatically for these supports based on the terrain model. As the terrain model is built up by borehole samples, the first step is to define these. On the Elements tab, there is a dedicated button to add borehole sample to the model. On the Add Borehole Samples dialog, two things has to be assigned to a borehole. First is a soil profile. Profiles can be started from scratch, loaded from the model database, loaded from the soil library, which is available across multiple models, or can be picked up from a position of the terrain model if we have that already. Now a new soil profile is created from scratch. Soil profiles are defined on the Soil Profile Editor dialog, where thicknesses of each layers and the type of the soil layer has to be selected from the soil database. For this particular soil profile, a 3.7 meter thick dry sand, followed by a 6 meter thick loose sand, and a 6 meter thick sandy gravel will be used. The second information to assign to a borehole is its location. This can be done by manual input of coordinates or using the pickup position from the model button. Clicking on the OK button, the borehole sample will be created in the modeling area, and the software will ask if additional boreholes are to be created or not. Click on Yes, and definition of new borehole samples can be continued. Visual representation of the created borehole object consists of the vertical tube, which depth equals the sum of the thickness of each soil layer, the color with which each layer is represented, and an orange rectangle which represents the plane of the terrain model. Since there is only one borehole available yet, it is a simple rectangle now. Soil profile of the next borehole will be loaded from the soil profile library, in which the thickness of the layers differs from the previous borehole. After adding the coordinates and placing this borehole in the model as well, the two boreholes will be connected with an orange line. This means that the terrain model now built up from these two boreholes, and the soil profiles between these two boreholes are interpolated. The definition of the additional borehole samples is speeded up as the process is the same for each. As new boreholes are being placed in the model, each acting as fixed points of the terrain model, are connected by triangulation. Within the triangles, the soil profile under an internal point is determined by interpolating between three soil profiles. Outside the convex hull of the terrain model, the soil profile is determined by extrapolation. Switching to any other view than wireframe view, the ground level of the terrain model will be visualized more heavily. Standing over a borehole with the cursor, an info window will show the layers, thicknesses, and the total depth. Graphical symbols of the boreholes and the terrain model can be turned on or off by choice from the bottom bar. To determine the Winkler spring stiffness of a nodal support based on the soil profile under that specific point using the terrain model, the support definition dialog needs to be opened. On the dialog, by clicking on the calculation button, we can get to the global node support calculation dialog, where we can set the parameters and the method of the stiffness evaluation. The new option on the dialog is the auto interpolate button. By turning the checkbox on, the software will evaluate the soil layer under the selected node and use the soil profile as input parameter for the calculation. If the support point is inside of a triangle of the terrain model, it will interpolate the soil profile between three soil profiles. If it is outside of a triangle, it will extrapolate the profile from nearby borehole profiles. As you can see, the z-directional stiffness of the support is overwritten with its new value. The same process can be applied in one step on many nodal, line, or surface supports as well. Selecting a bulk of supports, opening the calculation dialog and auto-interpolating the soil profiles for each, the dialog will show a range of stiffnesses which will be applied on the supports. Checking the info panel by moving the cursor over a support, we can see that stiffnesses vary depending on the underlying soil layer. Let's continue with the second approach, where after building up the terrain model, it will be used to create a 3D soil model, which together with the structure will form a coupled model. The coupled model requires a soil model containing data on soil profiles and depth. Soil model means that the superstructure is not supported by nodal, line or surface supports, but by the soil itself. Building a soil model requires the definition of at least one soil modeling domain, a new object type accessible through the Element tab. It is a planar polygon just like a domain used to model the surface elements, but it has a depth and its layers follow the stratigraphic model obtained from the borehole samples of the terrain model. Also, it can be meshed with 3D solid elements in the next steps. There are some rules when defining soil modeling domains. The size of the soil domain should always extend beyond the structure and should be significantly larger than the superstructure. The required dimensions, horizontal and the depth, depends on the stiffness of the soil and the structure, the load intensity, the stress distribution, and the deformation of the soil. It is advisable to choose the dimension of the soil model in such a way that further increases in dimensions do not lead to significant changes in the results. Because the module is not meant to handle the failure of the soil along slip surfaces, no vertical drop is allowed between connecting soil domains, and in fact the maximum slope angle is limited in 45 degrees. If the model contains at least one soil domain, under the Mesh tab there will be a new meshing option for volumetric mesh generation. The software can generate a volume mesh with the given average horizontal and vertical mesh sizes, considering all nodes and lies inside the domain. The solid element mesh is created by extruding the surface mesh vertically. Different types of meshing are available like triangular, rectangular, the combination of the two, and tetrahedron. In the case of tetrahedral meshing, the size and number of the tetrahedrals are dynamically adapting to the local soil layer thickness. If some layers are thinning to zero, the first three meshing methods may fail, so in these cases, choice of tetrahedral meshing is advised. The 3D solid finite elements are isoparametric, materially linear elements with 3 translational degrees of freedom per node. There are some rules to keep in mind when generating solid elements, Like the structural domains on the soil modeling domain is advised to be meshed separately. For design purposes, structural domains require finer mesh, while the soil can be meshed lighter, as the main focus is to get the deformation results and its effect on the superstructure. Modeling of pad strip footings are advised as pure column-wall connections on the soil are considered as singular zones. As for the boundary conditions, the bottom and on the sides of the soil model, nodes are rigidly supported in the normal direction and free in the rest. The results after the linear analysis are first and foremost are the deformations. Deformations are represented together with the deformations of the superstructure within the same result component. Soil stresses is a new result component including the axial strain in local x, y, and z directions, shear strains on local x, y, x, z, and y, z planes, the von Mises stress, S1, S2, S3 maximum, middle, minimum principal stresses, and the angle of the principal stresses. Soil strains, also a new result component, contains the axial strains in local directions, shear strain in local xy, xz, and yz plane, the maximum, middle, and minimum principal strains, angle of these principal strain directions, and the angle of the principal strain itself. As the current release is the first iteration of the module which will be followed by additional features in the future, it is important to highlight current limitations. Namely that the structure has to be lying on the ground, meaning that no basements can be modeled yet. Initial state of the soil cannot be taken into account directly. No slip surface is considered. The soil has linear behavior. Effect of the water cannot be considered yet. As soil module provides completely new type of calculation methods and possibilities non-existent in AxisVM before, we made several verification tests to ensure results are reliable and in line with the theory. All verification examples and models are public and can be accessed through our website. Next, let's check how the presented features can be used in AxisVM X7. The initial state of the model what we are going to use already has the same terrain model what was defined in the previous demonstration. This terrain model will provide stratigraphic data for the soil domain. The soil domain itself will be defined with an extended contour. Remember that soil profiles at points inside of the boundaries of the terrain model will be interpolated, while points outside of its boundaries will be extrapolated. Visibility of the terrain model can be turned off, so the polygon of the soil modeling domain can be selected a bit easier. Soil modeling domain function is located in the middle of the Elements tab, and by starting it, the contour lines of the soil domain polygon has to be selected. On the definition dialog, the local x direction of the soil modeling domain can be determined by reference elements or can be set automatically. The local z direction is always perpendicular to the plane of the domain. The local y direction comes from the right-hand rule. Soil modeling domain can take into account either all borehole samples or a selected sample. In the first case, soil properties are determined from the stratigraphic model. In the second case, the same soil profile is assumed at every position. Depth value of D is the minimum depth of the soil model. Clicking OK will create the soil model with the depth we have set before and the layers which are defined by the borehole samples of the terrain model. Layers of the soil profiles can be turned on or off by choice from the bottom bar. As mentioned in the presentation before, working with soil structure coupled model requires the modeling of footings with domains of their actual sizes instead of using nodal or line supports. Contact between the footing and the soil is created automatically. This example model contains some very basic loadings like self-weight and live loads for each story. Meshing of the structure and the soil is performed separately. In general, it is advised to use a more dense mesh for the structure, which satisfies design perspectives, and a lighter mesh for the soil, from where the main information is the vertical deformations and the effect of the deformation differences back on the structure. Right now, a tetrahedral mesh will be applied, as this is the most suitable type of element to follow the changes in thickness of the soil layers. The mesh size will be 4 meters both for horizontal and for vertical directions. Visibility of the soil mesh can be turned on or off individually. After everything is set, we can start the linear analysis and continue on how to evaluate the results. Checking the deformed shape and coloring, it can be seen that the highest deformations are where the loads and self-weight are concentrated in the core of the structure. Forming of the deformations can even be animated for a better visualization. Right now we only see the deformations on the outer surface of the soil domain. To check the results in the inside, we need to use section planes. Section planes can be created from the sidebar, from where their visibility can be controlled as well. Turning on a section plane, we can inspect each result component inside of the soil domain. The two new components are the soil strains and the soil stresses. Checking on the axial soil strain in local Z direction, we can see a distinctive region where strains are significantly higher. At the same time, comparing it with the soil stresses, axial stress in local Z direction seems to be decreasing quite continuously. Turning on the soil layers, we can see that the zone with the high strain is inside the middle layer. Going back to the parameters of the soil layer, we can see that this middle layer of loose sand has a much lower modulus of elasticity than the adjacent layers. Okay, so these were the steps we need to take in order to model the interaction between the soil and the structure. This approach can provide more accurate results compared to when the soil is modeled with springs. Consequently, the additional internal forces induced by relative settlements can be taken into account in a more accurate way. Design of structural elements and calculation of reinforcements is unchanged. The process is the same as it would be without the modeling of soil domains.